All right. So now we're going back to my slides just to do more examples of these. Is everybody good with the code? All right. All right. If you want to know the number of nodes, so let me just say again, we want our running time for these routines to be, well, speaking of running time for a minute, I heard what one of your problems was on the test. And for me, you should use dynamic programming, which could be in linear time, quadratic time, but you were expected to do recursive backtracking, which is exponential time. All right, so that pains me a little bit, just so you know. But we'll do that next year. All right, so here we want everything to be linear time, right? So that means constant time per node, right? And that means what am I allowed, when I'm the root, what am I allowed to do? I'm allowed to look at my value in my node. I'm allowed to make a recursive call to each of my friends and get a constant amount of information back. I'm allowed to combine their answers with the number in my root and send off my answer, right? So be sure never to do anything more than that, right? And I don't know if it's future slides or past slides, but if you need more information from your friends, it's okay to change the post condition so it returns more information, right? Then I'm getting more information from my subtrees, which helps me solve the problem I want. But then I also have to fill the contract, compute the extra information to give my boss, right? Whatever I ask my friends to do, I have to do as well, right? Everybody get that? All right, so in this case, we want to know the sum of the numbers, right? So we know we're going to ask our friend for the sum, right? What do you get from them? They're doing the same problem, right? They're giving you the sum of the left, and the other one's giving you the sum of the right, right? And then hopefully you all know how to put them together. All right? Right? Get your answers from your friends, and you add them together with the root. Right? Everybody get that? And then what's the base case? Well, I like the empty tree, right? So the base case could be, the code is, right? Right here n is pointing at some node. How do I know that I'm the empty tree? Well, this value is null, right? You don't go into it because it's null, but if this value is null, then I'm the empty tree. And then my answer, what's the sum of all the nodes in the empty tree? It's 0, right? And so then we have to say, here's just some good code, right? Everybody kind of, more or less, it's what Jackie was doing, right? Everybody kind of see it? You got to just change you bring in all those weird Java things, right? Any questions? Yeah? I'm going to go no. In fact, that code that Jackie gave us had an array of nodes, right? So I'm going to go, that's where he's going, right? Though later in the slides, he then switched over to binary, and it didn't add anything that we didn't do here, right? But of course, if we were doing binary, what we would do here is we would have a loop over all your children here, and you sum up all their answers, right? Does that make sense? Right? Here it's just, right? We take our program is sum. So we take sum of the left subtree and sum of the right subtree. And how do you get these trees, right? I'm here, I go to parent, right? So in dot children indexed, there's the fourth child, which always kind of weird to me, right, is now one of these, right? So I can say sum, right? Is that right? Always check particularly check everything I say, but definitely check my Java. Yeah.
Like a children is pointing to an array, and why is the first element pointing to another array?
Because we want 10 children.
It's the number of child, like those are the children.
Yeah.
An array of children.
Yeah.
But it is not an array itself. It's just like the
No, it's an array. You can have an array of fruit. You can have an array of integers. Yes. You know, maybe I'm doing you a disservice or a service, but in my mind, you know, n is not a node. N is a pointer to a node. But you can either say n is the node or it's a pointer to a node, right? So what is this? Well, that's what it is. It's either is this node or it's a pointer to this node, right? And then this one then points to another array, which points to another node, right? And the reason we have the arrays in there is so that you can have a lot of them, right? And so here, actually, it's not a bad question. If we were doing binary, we would do left child and right child, right? So this points to a node and this points to a node, right? So here's another option. What happens if I do child 1, child 2, child 9, probably need a child 0 because that's the way we do things, right? How would the code be if I did that instead of this? Yeah, sorry, say it again? Yeah, the word iterate makes me nervous. All right? So what's the advantage of this over this? You can iterate over here. I can have an I, right? This code here, I can have a loop. I equals 0 to number of children minus 1, right? And put in here an I. And then here I can put sum equals, are you allowed plus equals? Right? Takes a running total of these guys, right? But if I was doing this, I would have to have code for each of these, right? Which if I have 2 of them, I'm willing to do that. And if I have 10 of them, I'm not willing to do that. And if I have 100 of them, I'm definitely not willing to do it, right? Does that make sense? All right. So now we want to check whether your program works in all cases. So does it work in the generic case? Yeah, it was designed to work in the generic case, right? Does it work here? Well, you're going to get 0 plus this, right? It works, right? Does it work in this case? Right? Yeah, it works. And it's designed to work here, right? So it's just good to check that. Everybody get that?